All right, what do you need to do if you want to now include linear friction? Friction to your object. You know, your object will move up and down and it will continue forever, but in reality, there's friction. You want to add friction. So it's actually pretty simple because friction is just another force. So what you do, and this is according to Newton's laws of motion, you add another force. Friction is always anti-parallel to the direction of motion. Okay, and so the frictional force, you can add this with a negative sign. Okay, let's see, the mouse is working with a negative sign. Okay, so this is the so-called explicit approach. You just add a frictional force with a minus sign. So no matter what the sign of W is, the friction force is always opposite. Like if W is positive, you get actually a minus here. It will take away a little bit of that of vertical velocity. If W is negative, it actually adds a little bit. Okay, so it always reduces the speed, if you like. Okay, so now if you reformulate this, because in a computer code you can only have the unknowns on the left side of the equation and all the knowns on the right hand side. Okay, and this is how it looks like. The final equation is the same of what you had before, except for this bracket term. So you have 1 minus delta t times r. So it takes away a little bit from the 1 and it reduces the vertical velocity. It comes with a stability condition because the prediction doesn't make any sense if r times delta t exceeds r 1. Then all of a sudden you get a reversal of the friction force, which is absolutely bizarre. So you have a stability condition. Okay? The stability condition tells you your time step has to be less than 1 over r. To overcome that problem, you could use an implicit approach, which is shown here on the top right, where you formulate, sorry, the mouse is all over the place, where you formulate, instead of using n, you use the next level time step n plus 1, and you again reformulate the equation that you have everything that you don't know, which is your predictor on the left-hand side. And all that happens now is you have the same as you had before without friction. You just divide the entire right-hand side of the equation by 1 plus delta t times r. And this implicit scheme is always stable for any value. Okay. Technically, the unit of this friction parameter is 1 per second. You see, and this is what we call linear friction approach. So just before I show you how the simulation changes, okay, this is just how you formulate it in terms of your Fortran script. Okay, the only thing changed that you really had, you divide where the predictor is for the vertical velocity, you divide entire side, right-hand side, okay, by 1 plus r times delta t. You have to be a little bit careful. This is not fully correct because in Fortran you only have simple brackets. You don't have these higher order brackets. You have to be careful. So you're only very simple, the most basic brackets. Have a look at the sample code that I will give to you. Okay? So let's see how it looks like. This is a simulation that includes friction. Okay, and so over time, you see that the amplitude of your vertical oscillation actually goes to 0 over time. And this is what friction does. That the end image is not correct here. Okay. All right. So do you have any questions? Okay? You can ask your questions during our weekly Q&A session. Okay. All right. So thank you very much. Thanks for watching.